Hello dear students. So in continuation with our discussions on atmospheric thermodynamics, in today's class we will try to understand a very important concept in lower atmospheric physics. It is about the stability of atmosphere. So the idea is to introduce the concept of cloud formation. How does the clouds form, or what are the different types of clouds? What are the conditions in atmosphere that will be conducive for the formation of clouds? So before all these things, it's very important for us to understand what is the concept of atmospheric stability. So how does atmosphere being stable or unstable help in the formation of clouds? So in today's class, we will basically be understanding the atmospheric stability and its connection with the formation of clouds. Okay. So what we will do today is, let's say, so we will start with the basic idea of saturation or basic idea of vapor pressure. So we have already seen that we have already came across the idea of air parcel. So air parcel is an imaginary volume of air which is kind of adiabatic in nature. That means it's not exchanging any matter, or it's not exchanging any energy with the surroundings. And we also see that every air parcel maintains the same amount of pressure as the surroundings. So if there is an amount of moisture inside, we have seen that there is a limitation to which the air that is present inside this parcel can carry the amount of moisture. So it cannot carry any amounts of moisture, but rather the amount of moisture that can be contained in this particular air parcel is limited or is mainly decided by the temperature of this air parcel. So if you keep on changing the moisture content, there comes a point where the parcel will be at equilibrium, or the parcel will reach saturation. So at saturation, if you say, the saturation has also been explained in terms of with respect to the plane surface of water, and we have also seen what is saturation with respect to plane surface of ice. What the idea is, so the amount of vapor pressure that is exerted on the liquid surface or on the water surface decides how much amount of water vapor can exist. So saturation is the point where the evaporation is equal to the condensation. So if you consider, if you put water, liquid water in an air parcel or in a container, there is a constant rate of evaporation from the surface of this liquid, and there is a constant condensation from the gas phase to the liquid phase. So it's always there is a condensation which is trying for a phase transition between the gas to liquid, and there is always an evaporation which is the opposite direction. So these two things are most probably, or most of the times, they are in equilibrium. So the rate at which there is liquid that is trying to become gas is equal to the rate at which the gas is becoming liquid. So basically what you see is that even these two rates become equal, we say that the liquid is saturated, or the vapor that is there is saturated with respect to plane surface of water, if the water is what you have kept in this particular chamber. Okay, so saturation is when the evaporation is equal to the condensation. Now what will happen if you increase the water vapor content inside? That will lead to the formation of droplets, or that will lead to the condensation to prevail, and as a result you may see that on the walls of this container there will be tiny droplets of water, right. So basically the idea is, so what we are trying to do is, we are trying to understand the idea of saturation. So now saturation, you define it as the point when the amount of evaporation is equal to the amount of condensation. But this saturation is not defined just with respect to the amounts of vapor pressures, but we can also define saturation with several other parameters. Okay. Now, so at a particular point, there is evaporation that is equal to the condensation. But what generally happens is the amount of water vapor that can be held by this air parcel is very much dependent on the temperature of the air parcel. So that means that the higher the air temperature is, the more water vapor will be present in air at saturation. So, at saturation, no matter whatever the point of saturation is, at higher temperatures, the saturation is achieved at larger values of water vapor content inside the air parcel. So, this curve shows the temperature on the x-axis, and Es is the saturation vapor pressure, which is given in kilopascal. So, what you see is that the saturation vapor pressure increases as you increase the temperature. So, vapor pressure is the amount of pressure that is exerted by the vapor on the liquid surface. If there are more number of vapor molecules, gas molecules, H2O molecules in the gas, the pressure will be more, as simple as that, right. So, what it means, what this curve means is that if the temperature is more, if you keep on increasing the temperature of this particular container or this particular air parcel, the number of water vapor molecules in the air will increase. That means the air parcel is able to hold more amount of water vapor in it. So, that means that technically, so saturation is a point when the rate of evaporation becomes equal to the rate of condensation, and this point may also be dependent on the temperature, because as you go on increasing the temperature, the more amount of water vapor can be contained by the gas, right. So, then if this quantity, the amount of water vapor, if it is changing with respect to the temperature, then we have to define a parameter which measures the quantity, or which kind of quantifies the amount of water vapor that is present inside the air parcel, right. Then we define what is called as the relative humidity. A very important variable in atmospheric physics is what is called as the relative humidity. This is familiarly known as RH. So, relative humidity is the actual water vapor in air with respect to the maximum water vapor that could be contained within this air parcel. So, relative humidity, let us say you consider an air parcel. Now, you define the temperature at which this air parcel is present. Let us say you fix this temperature. Then at this temperature, what is the amount of water vapor that is existing at a particular point of time with respect to the maximum amount of water vapor that this air parcel can contain. The ratio of these two parameters will give you relative humidity. That means, let us say if you have 90% relative humidity, what it means in reality is that so there is still a provision of increasing the water vapor content by 10% or 15%. I mean, relative humidity can exceed more than 100%. So, the relative humidity is just the ratio of the amount of moisture or amount of water vapor that is contained in this air parcel to the maximum amount that can be put into this air parcel. Now, more importantly, the relative humidity now depends on two factors. What does it depend? The relative humidity depends on the actual amount of moisture in the atmosphere at any given point of time, and it also depends on the temperature. So, why does it depend on the temperature? Because the denominator, the maximum amount of water vapor that can be contained, varies with respect to the temperature. So, as you keep on increasing the temperature, the air gets the tendency to accept more amounts of water vapor into it. So, basically the actual amount of water vapor that is present in the atmosphere will decide the relative humidity, being the factor in the numerator, and the temperature which decides the maximum amount by varying the denominator. So, we have to remember that the temperature determines how much water vapor can be held within the air parcel at a particular condition. Okay. So, out of these two things, the main important thing that we should understand is, so saturation of course depends on the rates of evaporation and condensation, but the rates and the point at which these two things become equal are very much dependent on the temperature. So, there is no necessity that only at a particular value of temperature the saturation is to be reached. It can be reached at various different values of temperature. So, okay, now keeping these two things in mind, so relative humidity can be defined in a more different parameters, let us say. So, the relative humidity can also be defined as the vapor pressure defined by the saturation vapor pressure into 100. So, vapor pressure is, we have already defined vapor pressure. Now, vapor pressure can be defined at any given point of time, not only at the saturation. So, even before reaching the saturation. Now, let us say for example, you just keep a container and you keep water at the base of this container. Immediately when you keep it, there is an amount of vapor pressure that is existing inside this chamber. Now, if you allow sufficient amount of time to pass and if you allow saturation to establish, then at this point of time the vapor pressure that is exerted on the surface of this liquid will be different. Now, the ratio of these two things multiplied by 100 will give you the relative humidity in percentages. Or if you want to talk about mixing ratios, let us say mixing ratio is generally how much amount of a substance is contained in the total mixture. So, mixing ratio can also be used in defining the relative humidity, the parameter of relative humidity. So, relative humidity can be defined as the mixing ratio by saturation mixing ratio into 100. Okay, so, the relative humidity and saturation mixing ratio, saturation, condensation, these parameters are very well connected and we should always keep them in our mind. Now, we also define another very important parameter or very important temperature, which is called as the dew point. So, the dew point is the temperature to which air must be cooled in order to become saturated. Right. Now, one very important thing that we have been able to establish is that the amount of water vapor that can be held by the air parcel is of course dependent on the temperature, right. Now, then depending on the amount of water vapor, it can be more or less. So, let us say now depending on the amount of water vapor, we cannot say whether the condition of saturation is reached. For the saturation to happen, the amount of water vapor has to be of some ratio with respect to the total amount of water vapor or maximum amount of water vapor. Now, by changing the temperature, what you can do is within the existing limits, by not changing the amount of water vapor, just by changing the temperature, what you can do is with the existing value, with the existing amount of moisture in the air parcel, we can reach saturation. Right. For example, if you have 20% of moisture at a particular temperature. So, now let us say at a very high value of temperature, this 20% of moisture is giving you a relative humidity of something, let us say. Now, if you keep decreasing the temperature but not changing, let us say you take an adiabatic air parcel which is not allowing either inward or outward transfer of moisture from the air parcel, right. Now, you have 20% of water vapor within this. Let us say that now the temperature is 100 degree Celsius. Now, if you decrease the temperature, now 20% is not sufficient for us to call that the relative humidity is 100%. It is just, so relative humidity, that means the relative humidity is just 20% in this case. But if you decrease the temperature, what will happen? If you decrease the temperature, the vapor pressure will decrease. The vapor pressure, let us say E, will decrease. Now, if you keep on decreasing the temperature, there is a point at which with the existing value of moisture itself, you can establish the saturation. This particular point to which the air must be cooled so that its vapor pressure becomes equal to saturation vapor pressure is called as the dew point. So, dew point is generally considered as a better or absolute measure of moisture in the air, because dew point in dew point you're not changing the moisture content, rather you are just changing the temperature. That means because it does not change when the air temperature changes, because the amount of moisture is not changing. With the same amount of moisture itself, you are changing the parameter so that it reaches an equilibrium or it reaches the humidity of 100%. Okay. So, it only changes when the moisture content changes. So, assuming constant pressure, of course, right. For example, when the temperature is 30 degrees, so that when the temperature is high, the dew point is 10 degrees. I mean, so for this air parcel, by maintaining the same pressure, so when you say that you are maintaining the same pressure, you are not adding any gas or you are not adding any moisture content. Now, at this point, the relative humidity is just 29%. Now, if you decrease the temperature, if you decrease the temperature of this air parcel, the dew point is always at 10 degrees Celsius. Okay. But the humidity, relative humidity changes, because by decreasing the temperature, you are decreasing the ability of this ability of this air parcel to hold water. So, as you go on decreasing the temperature, at a particular point with the same amount of moisture itself, you have reached the saturation, right. So, this is the greatest advantage of using dew point as a measure of, let us say, quantifying the amount of humidity within the air parcel. Okay. So, the point is, when you keep on decreasing the temperature, at a particular point, with the same amount of moisture, you reach a relative humidity of 100%. Okay. Now, if you recap of the points that we have learned about saturation and various humidity variables, is that air temperature when equal to the dew point temperature, we say that the relative humidity is 100%. In terms of mixing ratio, when the existing mixing ratio of an air parcel becomes equal to the mixing ratio at the saturation or saturation mixing ratio, we also say that the relative humidity is 100%. And we also say that when the vapor pressure of the air parcel becomes equal to the saturation vapor pressure, then also we can say that the relative humidity in these cases should be 100%. So, to define relative humidity, you can define it in terms of temperature, you can define it in terms of vapor pressure, or you can define it in terms of mixing ratio. So, relative humidity becoming 100% means the temperature of the air parcel is equal to the dew point temperature, the mixing ratio inside the air parcel is equal to the saturation mixing ratio, and vapor pressure inside the air parcel is equal to the saturation vapor pressure. So, these three are the main methods or main criteria using any of which you can say that the relative humidity is achieved to be at 100%. Okay. Then, so now the thing is, by this mechanism, decreasing the temperature, you are reaching saturation, or by increasing the amount of moisture content inside the air parcel, you are reaching saturation, right? Or by changing the mixing ratio also, you are also reaching the saturation, right? Now, what is the point of discussing the saturation as such? Because saturation is the point when beyond which either you decrease the temperature or beyond which you increase the moisture, you try to increase the moisture content, the system will not accept any further addition of moisture into the parcel. That means, the system then develops a tendency to throw away the extra amount of moisture which is above the saturation values, right. So, that is why once the saturation is reached, if more water is added, that means if you are trying to add more moisture content into the air parcel, this will lead to the process of condensation. And what is the role of condensation? Condensation will develop tiny droplets of water on the, let us say, on the surface, or it will be thrown out, right. Now, what is the other way of going beyond saturation? Going beyond saturation, see, if you increase the temperature, you are just allowing the air parcel to accept more amount of moisture, right. So, if you increase the temperature, you are deviating away from the saturation. But if you want to go towards the saturation, the easiest way is to decrease the temperature. Wow. So, the point is, if you want to reach saturation, let us say, if you want to reach saturation by having more amount of moisture in this parcel, you can increase the temperature. The point is, if you want to reach saturation by adding more amount of water vapor into the air parcel, you have to increase the temperature. By increasing the temperature, you are increasing the ability of the air parcel to hold more moisture. Now, if you do not want to add any more moisture, rather you want to attain saturation with the existing amount of moisture itself, then you have to decrease the temperature. So, these two conditions they work. One method requires more amount of moisture to be physically added to the air parcel. Another method do not require physical addition of moisture, rather it requires decrease of temperature, right. Both of these cases will allow the air parcel to become saturated or supersaturated. Once the supersaturation is reached, it will throw out the extra amount of moisture beyond saturation outside, and this happens by the means of condensation, and condensation will release some amount of latent heat. That is a different story, right. Now, so basically, so it will lead towards the condensation, and the vapor when condenses to form tiny droplets in the atmosphere is generally called as the phenomenon of clouds, or the phenomenon of cloud formation itself. So, what is a cloud? Cloud is a collection of tiny particles of water or ice which have condensed from the gas. Right. Now, one more important thing is that for the formation of droplets, the saturation has to be several times larger than 100%. So, what it means is that if you want cloud nuclei, or if you want the cloud droplets to form out of moisture, you will need particles. These particles will act as the platform over which condensation will happen, and these particles are generally called as are called as the cloud condensation nuclei. CCN is cloud condensation nuclei, right. Now, so clouds will only form when there is saturation that is reached and when there are enough number of cloud condensation nuclei present in the atmosphere, right. So, why are we discussing this? We have seen the methods by which you can reach saturation. Now we are seeing what will happen once you reach saturation, right. So, now in summary, to make a cloud we really need three things. We need moisture, of course, we need cloud condensation nuclei, and we need a method of cooling the air to saturation. So, that means that, like I said, by not physically moving moisture into the air parcel, with whatever the moisture content that is available in the air parcel, the only way to reach saturation is by decreasing its temperature, right. So, what you are doing is the bar of saturation is here, right. So, now if you the bar of saturation says at least this much amount of, let us say, X amount of moisture is needed for the saturation. Let us say X amount of moisture is needed for reaching saturation. So, this is the bar of saturation. This is what is called as the bar of saturation, right. Now, what you can do is you rise the amount of moisture from here to here, right, or you bring this. So, this is the amount of, so at any given point of time, this is the actual amount of vapor pressure or actual amount of moisture. Simply speaking, when the actual amount of moisture becomes equal to the saturation moisture, you can simply say that you have reached the saturation, right. Now, the bar of saturation is held at this position only by the virtue of its temperature. So, if the temperature is very high, this bar will go even further. The easiest way to put it is X grams of water vapor can be held in this air parcel at a particular value of temperature. Okay. Now, at the same value of temperature, you do not have X grams of water molecules inside this air parcel. Rather, you have only, let us say, X minus, let us say, few units, X minus Y units of water molecules inside. Now, what you can do is either you you keep putting water vapor physically and you rise this to here, or what you can do is, if you decrease the temperature, the amount of moisture that is present, the amount of moisture that can be present in this air parcel comes down. What you are doing is, by decreasing the temperature, you are just bringing the amount of water vapor that can be held by the air parcel to the level that the amount of moisture that is actually present in the air parcel, right. So, now like this slide says, to make a cloud or to allow condensation to happen, you need three important things. One, when the saturation is reached, the excess amount of moisture will try to condense, and for this condensation to happen, you need particles, tiny particles, which are called as cloud condensation nuclei. You physically need this. I mean, these particles are supposed to be existing at, let us say, 5 to 10 kilometers altitude, and only on the top of these particles cloud condensation will happen. The droplets will form invariably. This is a must condition. Okay. Then now you need a method by which you can decrease the temperature of the air parcel, right. So, you are simply decreasing the temperature. So, decreasing the temperature of the air parcel is the main method by which clouds are formed. So, clouds, I mean, moisture is there, of course, and cloud condensation nuclei are very much present everywhere in the atmosphere. Tiny particles, like we have seen in the beginning or introductory classes itself, that the atmosphere also allows tiny suspended particles to be existing in it, right. So, that means that the only method or the only process by which clouds form is by rising an air parcel or by decreasing rising an air parcel to an altitude which is very low in temperature, or by decreasing the temperature of the air parcel. Okay. Now, the formation of cloud is mainly dependent on this particular aspect in which you rise the air parcel to an altitude where the temperature is very, very less, or you decrease the temperature of this air parcel. Right. Now, let us talk about the condensation nuclei. So, what are these condensation nuclei? So, these are called as cloud condensation nuclei. Okay. The water vapor needs a surface on which it can condense. So, that means that when the relative humidity reaches 100 or tries to become over than 100, it needs some particles over which it can condense. The condensation nuclei are very small, very tiny, which are very, very small in the sense their diameter is typically of the order of few tenths of micrometer. And there must be these particles must be solid particles in the air which are suspended in the atmosphere. And there can be many different types of condensation nuclei. So, let us say suspended particles of atmospheric dust, mineral particles, ash from the fires and volcanic dust, microscopic organisms as well, and vaporized meteors. So, meteors when they enter the atmosphere, they will burn up and they will create a lot of ash and the presence of metallic species in the atmosphere. All these things can serve as condensation nuclei. So, their role is just to act as a platform over which tiny droplets of clouds can form. And one more example could be the salt that is sprayed into the atmosphere from the tides from the oceanic waves. Okay, right. Now let us see what is the main method in which you can actually form clouds. Okay, we have learned few aspects about saturation. What are the variables which can be used to define saturation in terms of mixing ratio, in terms of vapor pressure, or in terms of the amount of moisture content that is available, right? And if you have, we have understood the concept of relative humidity, how it can be used to define saturation, and what is the role of temperature in defining the conditions favorable for saturation. Then we went on to discuss what will happen once you reach saturation. So, everything is going towards understanding the formation of the clouds or the physical process which will be followed in the formation of clouds. Now, at the end we have realized that for the formation of clouds we need three important things. We need moisture, of course, which condenses and forms a cloud, and we need a solid surface over which the moisture can condense. And thirdly, and the most importantly of all the three things, we need a mechanism by which we can decrease the temperature of the air parcel so that it allows condensation to happen. Okay. Now, in the next class, what we will try to understand is what are the different ways in which you can rise an air parcel, or what are the different ways in which you can decrease the temperature of this air parcel. That will be the topic of discussion in the next lecture. Okay. Yeah. Thank you.